Yeah, so I think this presentation will follow very well from Brent's. What I want to talk about is really how can we use vision, computer vision and human vision, to contribute to this revolution we're seeing and how we can understand our urban environments in 3D. The first point I want to make is that vision is actually almost a poster child for a problem in big data. And so what do I mean by that? So for example, take this brave soul who's skiing down this mountain. Well, in order to not harm themselves, they have to process the information that's impinging on their two retinae, each of which is receiving about 10 megabits per second, so 20 megabits per second total. And so if you integrate that over time, by your age, roughly speaking, you'll have already processed about 2 petabytes of data. That's a lot of data. And so in order to be able to use this sense of vision, you really have to understand all of the principles of big data management. How do we take this fire hose of information and crush it down into the useful nuggets that we can actually act on? And whether you're talking about the human visual system or a machine vision system, we're always dealing with a system with finite resources, both in terms of computation and bandwidth. And in the human case, of course, you have a fixed cranium. So although your computer here is very powerful, it's not infinitely powerful. And of course, we could have tried, in evolution time, we could have evolved a bigger brain, but that would have led to lots of social stigma and other unpleasant things. And so there's pressures on those resources. And similarly for machine systems, sometimes we can afford a very powerful supercomputer, but as Brent was describing, we want to also deploy applications on handheld devices that you can use to help you, through your day. So we have to figure out ways of running applications on limited computational resources. So in my lab, the approach we take is what we call biologically motivated computer vision. So we're trying to better understand the human visual system as a very powerful visual system in order to build better machine vision systems. And this is the crew here that does all the real work. And I'm sure you'll meet some of these people in these 3 days, and particularly the ones that are giving presentations this afternoon. So the basic idea is reverse engineering, right? If you want to build something, one of the first things you want to do is, well, are there any other existence proofs of this thing I'm trying to build? And if there are, let's try to understand how they work. Okay, so I want to spend a few minutes outlining how we do this. So the first thing I want to do is just talk about some principles we think are important for human perception that we are trying to invest into our machine vision systems. Then I'll talk a bit about the application domain that we're currently focused on to explore these principles, and finally just some comments on a few technical advances. So principles. So what I want to do is articulate 3 pretty fundamental principles that we think really govern how the human visual system works and that we think we can use to build better machine vision systems. So the first of these we could call knowing where to look. That is human attention. So a really important thing about your visual system is that it's not static, it's not passive, it's very active. So as I'm giving this talk, I'm constantly moving my head and eyes to look at you or to look at my screen. And why am I doing that? Well, it's partly because I can't see behind my head, right? So if I want to look at the screen, I have to move my head. But it's also because my retinae are not uniformly sampled, right? I have only a very small central portion of my visual field where I have high resolution. So if I want to see your expression and see if you're enjoying the presentation or you're maybe a little confused, I can't do that if I don't look at you. I have to direct my eyes at your face, okay? Now, having said that, I still have a wide field of view, and that's sufficient for me to detect if someone walks in the room or someone delivers the much-needed coffee. But if I wanted more detail, I would have to move my head and eyes. Okay? And so, well, why are we doing that? Well, because we're trying to maximize the utility of the visual information that we're processing, right? So we want to put our eyes where the information is valuable for the task at hand. So if we had tried to replicate that really high resolution over our whole visual field, then we'd have this enormous cranium, as I mentioned before. So we're trying to, in evolutionary terms, I guess, the human visual system has evolved a solution where it gives us that high resolution, but only in a very narrow field. But it gave us this great ocular motor system where we can move our eyes really quickly to optimize where we place those photoreceptors in the visual scene. Okay? And this is just an example of how that would work if you were watching a news broadcast, for example. If this person is speaking, I would tend to look at them, and they're in focus, so high resolution, I can see their expression. This person's face is now out of focus because I have lower resolution here, but that's okay because it's this person I care about. Once this broadcaster begins to speak, then I'll fixate on that person, and then I'll be able to see their expression. So something we're very interested in is building machine vision systems that have this capacity, and I'll point out some of that research in this lecture, and then in the lab tours today, I'll show you some examples of what we're doing. The second principle that we think is foundational for human perception and that really connects with Brent and Gunho's lectures was the fact that humans see in 3D. Okay? Now, that only makes sense. You live in 3D, at least I hope you live in 3D. And that's the world in which you have to survive and thrive, right? So you have to understand the world in 3 dimensions. So you might think, well, okay, I know that because you know, sometimes I go to stereo 3D films, right? And so the way that the human visual system sees in 3D is we have 2 eyes, and we can triangulate and get that lost dimension, okay? But I want to point out that that's not the only way that you see in 3D. So for example, if you close one eye, it's not like you suddenly think you're looking, you know, at a painting. You still understand that the world is in 3D. There's many cues that you use in order to see the 3-dimensional world. And these cues are really innate. You can't really control them. And this is a great illustration of that from Roger Shepard. When I show you these 2 tables, you can instantly see that they are completely different in shape and size, right? But what's interesting is they're not. So in fact, I can take this quadrilateral here, and I can simply move it to the other quadrilateral by rotating and shifting it in the plane. And you can see that, in fact, they're exactly the same size and shape. Okay? So this seems, and if you don't believe me, you can come up with a ruler later and verify. Okay, so what's going on here? It seems like a contradiction. They're clearly different, but they're clearly the same. So what's going on? Anybody have any suggestions? It seems like both of those things cannot be true. Right? Okay, well, the answer is that they both can be true because they're true in different dimensions, right? So what I showed you was only that these 2 quadrilaterals are the same in 2 dimensions, right? And that is true. However, you don't really care about that. Your visual system really doesn't care because you instantly see these tables as 3-dimensional objects sitting on a common ground plane. And as 3-dimensional objects, if you were able to walk into this 3-dimensional world and stand on that ground plane, in that 3-dimensional world, these 2 tabletops would be completely different in their size and shape, right? It's only on projection to the image that those quadrilaterals become the same. But you really don't care about that projection. You care about the 3D world because that's the world that you live in, and that's the world you have to survive in. Okay? So we just heard from Gunho and Brent about, you know, the importance of 3-dimensional modeling of our urban environments, and that's fundamental to our collaborative research program. We want to be able to build technologies where we can understand what's going on in the 3D cityscape. Okay, and then the final principle that we think is really crucial for human perception is the ability to adapt. So you've all heard a lot about the revolution in deep learning in the last 5 and 10 years. That revolution, though, has been focused primarily upon what's called supervised learning. So we have very large labeled training data sets that we use to train up these deep networks. And once they're trained, the weights are fixed, they're frozen, and then these networks are deployed. They don't learn after that, okay? It's like, you know, maybe you know an older person who you think has just stopped learning. That's what these deep networks are like. But in fact, human perception is not like that at all. We're constantly adapting, constantly learning, constantly optimizing for a new environment, okay? in many different ways. And I could show, if we have time, I could show this just kind of extreme example as far back as the late 19th century. This is online. You can see this on YouTube. Oh, except it's not playing for some reason. OK, so I won't show it to you now. Unless I drag this. Can I drag it? Oh, there we go. OK. So this is an old video from Kohler showing the first experiments in which they introduced prism glasses that optically inverted the visual world. They tried to understand what that would do to a human observer. And of course, there was a while in which these human observers could not actually function, and they would, I don't know if I can bring us to the right part of this video, but you know, when something would be held high for them, they would reach low and so forth because they had not yet adapted. But what's remarkable, if I can, sorry, I can find the right parts of the video, is that there. Well, so that's what they are supposed to see when they're unadapted. But with time, they actually adapt, and let me bring this back, are able to actually adapt to the fact that the world has inverted. Maybe I won't show this because it's taking too long to swap back and forth. But the point is to say that, go back to my screen here. There we go. OK. OK, I have to kill this. There he is riding his bike. OK, so he's a very happy camper now. He's completely adapted to his inverting goggles. So not that we want to put inverting goggles on our machine vision systems, but the point is that the human visual system is remarkably adaptive. We don't normally have to go that far. We don't normally have to understand the world upside down. But there's a lot of geometric and photometric transformations and different types of contexts that we have to adapt to. And unless we imbue our machine vision systems with that ability, we'll find that they're very brittle. They'll work in the environment that they're trained in, but when we try to deploy it in the real world, they will not work. OK, so those are the three principles. Let me try to now describe this application domain in which we're trying to apply these principles. So I'll start with this motivating quote from our former Minister of Transportation in Ontario, referring to the problem of gridlock, estimated to cost $6 billion a year just in the Greater Toronto and Hamilton area. Okay? So for those of you who are drivers, you've all experienced the joys of this gridlock. And it's one of the things that motivates us to try to better understand how we can use intelligent systems to better manage urban mobility, how we get around in cities. But it's not the only motivating factor. So in addition to that cost, there's also the cost to the environment, right? So it turns out that the transportation sector in Canada is actually the largest contributor to greenhouse gas emissions. And there are other factors as well. So for example, accessibility. I know this is one of the things that ESRI Canada is interested in, and that York, for example, is interested in, is how can we design our spaces so that they're more universally accessible, whether people have motor or cognitive deficits. The number of people that have various kinds of disabilities is increasing, partly due to the demographics of our city and our province. So many reasons why we'd like to be able to improve how people can get around in our urban environments. So this has led to a new project that Brent mentioned. We call Intelligent Systems for Sustainable Urban Mobility, or ISUM. The project just started a couple of months ago. It's a 5-year project. It's collaborative. It involves a number of academic researchers, including myself and Gunho San and Petros Faloutsos here at York, and also 2 researchers at Waterloo, a number of companies, including ESRI Canada. And the objective is to research and develop integrated, key focus on integration, intelligent systems for sensing, analytics, simulation, and 3D visualization of urban mobility. Okay, how people are getting around, whether they're driving, using public transit, or walking. And some of the things Brent showed show that we've gone a long way already in developing these technologies. We, I mean, as a planet. One of the things we're focused on here is how can we use visual information more to increase the power of these technologies. And the second aspect of that is the visualization component. So Brent showed that beautiful 3D dynamic visualization of the city of Toronto. The reality is that in a lot of our facilities, that's not what we have. If you walk into a standard security office, for example, the one we have at York, we have more than 600 cameras distributed throughout the campus. But instead of a 3D model, this is what they see. They see a wall of TV monitors, each of which has a number of different projections of that 3D visual world. And so we've just seen how humans perceive the world in 3D. For a human to make sense of what's going on in a complex environment from these disparate 2D projections is very difficult. Similarly, for if you walk into the current Ministry of Transportation Ontario traffic control office, you see a very similar thing. So the issue is if something happens that's complicated, let's say there's some kind of natural disaster or something, it'd be very difficult to really figure out what's going on from this kind of pastiche of information from different projections. So visualization is a really key part of the ISOM objective, which is to deliver more natural, more complete, three-dimensional visualizations of urban environments, and particularly the dynamics. So I often show this slide as kind of the vision. As you've seen from the previous two presentations, we have enormous power now in 3D geo databases, but they're largely static. At the same time, what I'm saying is that we also have incredible existing infrastructure in terms of video cameras throughout our urban environment. We have this at York, for example. The Ministry of Transportation has a camera every kilometer along the 400 series highways. The City of Toronto has their own cameras, but they're two-dimensional, right? So the vision is really to merge these two things to create a three-dimensional and dynamic system for urban awareness. And as Gunho mentioned, a few years ago, we developed a proof of concept of this idea that we call 3D Town. Now, in many ways, it was quite primitive. It was based upon a Google Earth substrate that wasn't really optimized for this kind of dynamic rendering. But I think it was sufficient to show people the vision of using video data. So in this case, this is a standard surveillance camera at York University in the York Common, if you know that. To use computer vision algorithms to detect and track what's going on, so vehicles and pedestrians. And then to make use of this 3D model, in this case the model developed by Gunho and colleagues, and use our algorithms to back project these events back into our three-dimensional model and populate that model with avatars that represent those dynamic agents in the scene. And that allows us to now visualize what's going on, not in the two-dimensional plane of the image, but in the three-dimensional model of the world. So that's where we're heading. This is, as I said, proof of concept. What ISOM will do over the next 5 years is bring this much more into the next generation in terms of using modern gaming engines, Unity 3D, taking advantage of other sources of data as well as vision. Okay, so just for the last few minutes, I'll just mention some technical advances that we're working on without getting into too much technical detail, but just giving you a sense of some of the research areas. So first of all, we talked about looking at the right thing, or visual attention. So we're developing constantly better attentive vision systems, machine vision systems. We'll show you some of those in the lab this afternoon. The basic idea, I mean, we could try to recreate the human eye. That it has many technical challenges. So what we do instead is try to create an attentive machine vision system in a way that's convenient for machine vision. Typically what we do is we take two cameras, one with a wide-angle lens so it can see a whole environment. So for example, if it was in this room, we make sure it could see the whole room. And we take a second camera which has a longer focal length, so a much narrower field of view. But we mount that on a pan-tilt platform so it can move around. So the idea is to get these two things working together just as your peripheral and your central visual system work together. So an example is shown. I think this video is not going to run. Plagued by the codecs problem. Let me just see if I can. Okay, unfortunately I have the same. How did we find my mouse? Oh, there it is. Okay, just one second. No, too bad. Okay, well, that's just as well. So you'll see it this afternoon in the lab. So what this would normally show is the attentive, so the pre-attentive camera is showing you the entire room. The attentive camera is now moving around to look at people's faces. So at the pre-attentive resolution, you can't really recognize people or recognize their expressions. So the attentive camera is sampling people's faces and providing that resolution that you need to identify what they're doing. So that's the visual attention principle. The other principle I mentioned is seeing in 3D. And so there are kind of two aspects to ISOM. One is the integration of video sensing with three-dimensional models that we've built of the environment. One issue is that in order to do that, we need to be able to know what the pose of the camera is relative to that three-dimensional environment so that we can back project those events and populate the 3D model with the appropriate avatars. The second mode of operation is what if we don't have a 3D model or that 3D model is incomplete? So we're very interested in being able to figure out from just a single camera what some of that three-dimensional structure is. So you might say, well, okay, how would I do that with a single camera? And what I would ask you to remember is that in the early Renaissance, painters figured out that they could use the cue of linear perspective to provide a really compelling three-dimensional experience of a painting, although it's painted on a flat two-dimensional canvas. Okay? So that tells you that your brain is able to use more than just stereoscopic 3D to appreciate the 3D world. We're able to make use of this very powerful cue called linear perspective. So a lot of our work is about using linear perspective cues in order to understand the orientation of the camera relative to the scene and also to be able to recover three-dimensional properties of that scene. This is particularly tractable in urban environments where we often have what we call a Manhattan frame, which is an orthogonal coordinate system defined by the right angles of buildings and roads and so forth. So we do a lot of work on that, a linear perspective problem. We have the most widely used database that's used in this research domain called York Urban DB. You'll be hearing a bit more about some of that research work from one of my graduate students this afternoon, Yiming Chan. I will just say briefly that one of the major advances we made in this work is understanding the importance of squeezing redundancy out of imagery in order to make accurate estimates. What I mean by redundancy is that it turns out that if you just have the contours of an image, that's typically sufficient to give you all of the information in the image, that you can essentially recreate all of the pixels from those contours. And so it turns out that that's quite important in order to get accurate estimates of three-dimensional information. If you try to use all the pixels directly, then one tends to get lost in a lot of noise. And so that's one principle we found to be important in this work. Okay, and you'll see more. I won't talk more about this. You'll see more about this this afternoon. Now, finally, I'm sort of running out of time, so just let me mention a few of the applications here. So one is in terms of understanding traffic flow. And here we have a challenge that we don't typically have a really strong 3D Manhattan frame. You know, we tend to have very clear lines along the highway, or curves if it's a curved highway, but we don't often have a lot of vertical structure or structure going the other direction. So we've developed specific techniques that can make use of this parallel structure in order to recover the ground plane orientation and therefore make measurements of the traffic in ground plane coordinates. So the idea here is, if you want to understand, I was talking about measuring traffic speed. If I tell you that the traffic is moving at 5 pixels per second, that's not of much value to you, right? That's a two-dimensional measurement. What I need to do is tell you the traffic is moving at 80 kilometers an hour. And to do that, I need to back project the video information back to the ground plane, okay? And again, I have a video here that's not working, but I can show you that in the lab tonight, this afternoon. Okay, we have techniques that can also be applied where we don't have really any structure, no lanes or no strong 3D structure, that uses the motion of people on the ground plane. This video is working, so I can show you a bit about that. So in this case, we don't have a lot of that structure, but we do have agents moving around, although they're not moving in straight lines or anything. It turns out we can use the statistics of that motion to, again, understand the orientation of the camera and then be able to make accurate judgments of speed. And then just very quickly, we're using all these technologies to do things like measure traffic volume. So this involves using this three-dimensional knowledge of the pose of the camera in order to be able to model objects as three-dimensional, using very simple approximations, in this case as cuboids, but it turns out that's sufficient in our case to be able to do a much better job of segmenting objects we see in the image into the appropriate vehicles in the appropriate categories. So that's this video shows an example of that system where we have a camera that's running, monitoring this traffic, extracting these segments in 2D, modeling them in 3D, and then actually counting the number of vehicles in each lane. Okay, I'll skip over the generative model. I'll show you that this afternoon. But finally, we're also working on crowd analytics. So people that are walking or standing in the environment. This is important and connects to what Brent was saying about crowd modeling. It's very important for safety and security, for management of events, to understand, and also for planning, to understand how many people are in the visual environment. This is a project where the importance of adaptation has become most important. Pretty much all of the prior approaches to this problem use supervised learning, which means that they work on the data sets on which they're trained, but if you try to apply them to another situation, they don't work. So the innovation here was to develop a completely unsupervised method that will adapt to new environments. The core of that is a 3D simulation where the system learns in its current environment how people in the three-dimensional environment would appear in the image. And I have a quick video of that simulation. So again, we're using very simple three-dimensional models, in this case spheroids, oblate spheroids. Each person is represented simply as one of these standing on a ground plane. We learn how those three-dimensional models project to the image as clusters. Then we learn how to estimate the number of people from the properties of those clusters, their size and their shape. And the remarkable thing is that although the system is completely unsupervised, it can learn to accurately track the crowd flow over very diverse data sets without having to have any supervised labeled training data. All right, I'm out of time, so just to summarize, it's a very exciting time for us because we are getting a chance to work with academic collaborators in diverse fields, computer graphics and geomatics, but also industry collaborators who are in Canada and really doing cutting-edge applied work. Our goal is to try to bring to the table these principles we've learned from human perception and try to build better intelligence systems inspired by those principles. Okay, and that's all I have to say. Thanks for your attention. Okay, so if there's any quick questions, I could take them now. Otherwise, I'm happy to just say, let's have a break, and then you can approach me individually if you have any questions. John Hong. What's that? The encoder? Oh, it's getting colder. Do you think I turned it the wrong way? All right. Maybe I'll ask Irina maybe at the break to see if she can find out if there's a way of controlling the temperature. Any other questions? Brent.
I just have a question about the traffic monitoring. How readily connectable would that be to something like a web stream of the sort that I showed you in the Toronto Live app?
Yeah, I think it would be very connectable. I mean, we're using MTO cameras here, not City of Toronto cameras, and so I'm not actually sure what their network is like, but I presume it's similar.
Yeah.
You know, a lot of this is logistics, right? Getting the agreements in place to have the access to feeds.
Right.
MTO is similar to City of Toronto, so they make available their feeds on like a 5-minute kind of
delay
update, right?
Yeah.
But in reality, of course, they have frame rate coming into their office.
Mm-hmm.
And so one of the things we're working with MTO about is to get that frame rate bandwidth into York so we can really develop these real-time technologies. So video is very complementary to using GPS or cell or Bluetooth,
right,
in the sense that those are all samples, right? So it's not fully subscribed, so you get a sample of the population of vehicles, whereas video will give you 100%, and also can give you much more information, more detailed.
Right. I mean, you could differentiate between trucks and cars, for example.
Right, right.
Yeah.
So currently our system differentiates 4 different categories of vehicle based upon just dimensions, but we would like to do much more fine-grained recognition. I think
it's great. Yeah, thanks.